Hello, and I'm Vitos, and you are with Vitos Academy, and today I'll be showing you Cramer's rule, which is a solution of a system of linear equations, or if you are more interested in what exactly this rule is doing. Pretty much imagine that you have a linear equation like this: 82x1 plus 45x2 plus 9x3 equals 1, the one I'm reading right here. And then the second row looks like 27x1, 16x2 plus 3x3 equals 1. Then 9x1 plus 5x2 plus 1x3 equaling 0. Then you don't have to think anymore how much is x1, x2, or x3, or you can call them a, b, c, or x, y, z. As in my case, you can simply do the following. You can create three determinants. Pretty much you write the whole system like this: 82, 27, 9 in a matrix, then 45, 16, 5, writing just the coefficients, then 9, 3, 1 like this. And as additionally, you draw a line like this and you write 1, 1, 0. Further, you continue calculating the determinant of a1 divided by a, and this would be equal for x1 for this one here. So in this case it's found to be 1, and if you sum all this, 82 times 1 plus 45 times 1 as well plus 9 times minus 14, it will be equal to 1. Okay, so the idea is to show this into Python, and just to show you and to walk you over, this is what should be the final result of the code. So we have the coefficients here, we have the results, we do some magic, and we see that it's 1, 1, minus 14, solution found. So let's start. And starting, as I said, it's really simple. I mean, you just calculate 4 determinants, then you say, okay, the first one, x1, the first variable that we're looking for, is equal to determinant a1 divided by determinant a. The second one, a2, is equal to determinant a2 divided by determinant a. And the third one is determinant a3 divided by determinant a. So now the great question is, what exactly is a determinant and what can we do with it? So let's take a quick look in Excel. In Excel, we just have a matrix like this. So we can say, okay, this is our x1, this is our x2, this is our x3. And we simply copy 82, 4, 27, and 9 like this in a row. Then 45, 16, and 5 like this. Then 9, 3, and 1 like this. And we just think, okay, what exactly can we do in order to have a determinant? We can use an Excel formula that just takes the matrix 3 by 3. That would return us 1. Is it really 1? It is, yes. Determinant A is 1 everywhere. Like you can take a look, it's here, and it is here. How exactly did we calculate determinant A? Calculating a determinant is really an interesting thing, and I'm going to do it just once, and then I'm going to use Python code for it. So bear with me. Pretty much what we should do is the following: take this a1 here, and then multiply it by the difference of this times this. I wouldn't be using yellow. Minus that times that. Yes. So we do this, then we do this, then we do this, but it should be like should be a bit different. Then we take this one and we multiply by that difference, then we get that one, and we multiply by that difference. I will start showing you with Excel how it looks. Hopefully at the end I would get to 1. So let's see. First remove this one, and say, okay, we have A1, this one, multiplied by B2 times C3. And then the difference of this times that. Okay, I don't need so many parentheses because the PEMDAS rule, if you come from the US, or it's the normal rule that you probably know just because you went to high school if you come not from the US. Yeah, okay, so we'll leave 82 here, and now I will do the same but a bit different for each one of those. So it's 45, and then it should be like this. Not exactly. No, 0 is okay. And then we do it once more, but like this. Yeah. So yeah, and in the end, what we do with these numbers is really important. We do 82 minus the second one. The second one is on the B, plus this one. And we get the 1. So pretty much this is how the determinant is calculated. But that's not all. As you see, here we have something called determinant of A1, determinant of A2, and determinant of A3. Which if we take a look here, we would see that they are all 1, but the determinant of A3, which is minus 14. So what I'm doing is I'm just going to copy this one. So for the determinant of A1, pretty much whatever we should create is the following. We replace this first row with 1, 1, 0, the second row with 1, 1, 0, and the third row with 1, 1, 0. Is it correct? No, it is not. Let's go back in Excel and think, okay, we want 1, 1, 0 like this everywhere. Okay, and we saw this one. So pretty much what is important is to remember, simply replace this one, because this matrix here, the green line is what we are interested in. The green row, the green column is what we have replaced. 1, 1, 0, 1, 1, 0, 1, 1, 0. The same thing we should be doing for determinant 2. This is the old one that I have copied the original one. So it is like this: 1, 1, 0, 1, 1, 0, and then 1, 1, 0. And it is 1 as well. So all these determinants are 1. And this is kind of expected because we have 1s here. Now with the determinant 3, we do pretty much the same thing. We replace 1, 1, 0 on this one, 1, 1, 0 on this one, and 1, 1, 0 on this one, and it's minus 14. So this is how we get all these values, 1, 1, and minus 14. Then at the end, we get 1 divided by 1, 1 divided by 1, 14 divided by 1 here. And this is how we get x1, x2, x3, or in the other way, x, y, and z, as you probably see them usually in the mathematics. Now, let's see how we do this in Python. In Python, pretty much what we should do is, yeah, I'm using Jupyter Notebook, and I'll be creating a matrix with 2 dimensions. The first dimension would be, of course, the rows 82, 45, 9. It's the coefficients 82, 45, 9. Yeah. Then second is 27, 16, and then 3. Great. The third one is 951. Like this. And if we of course ask for the coefficients, we'll see them clearly. So 82, 45, 9, 27, 16, 3, 951, 951. Yes. And I'll introduce a second one, it will be called results. It will be equal to 110. And if we want to call it, yeah, that's it. So the beautiful part starts with two things we need to solve the Cramer pretty much method, or solve the solution of, find the solution of a system of linear equations using the Cramer method. So how do we do it? First we would make a way to calculate the determinant of a matrix. I'll call it 3 by 3 matrix explicitly, so we don't need to check anything. And result equals 1, return result. And now starting to think, what did we say? Pretty much matrix 0, 0 times matrix 1, 1 times matrix 2, 2. So this way we made this cross. This is the 0, 0, and this is 1, 1, and this is 2, 2. Pretty much. And that one minus matrix 2, 1 times matrix 1, 2. And to cut it over for you, I'll really write it quickly. So this is how it looks like. What is important to remember is this signs here. It's first minus, then plus. If it is 4 by 4, we would have a minus again, and if it is 5 by 5, we would have a plus again after the minus. So it's like this, minus, plus, minus, plus, minus, plus all the time. Yeah. Let's introduce Cramer method with coefficients. I'm just using the tab, so I hope it would help, but it is not. Rent results. So pretty much I'm just writing here d equals 1, d1 equals 1 just as a placeholder, d2 equals 1, and d3 equals 1. So once I know this, how they are, what I'll do is I will have the general determinant of the matrix. This is this A here, the general one, and it will be determinant of 3 by 3 matrix, and I'll be passing D. Then we have the rest, determinant D1. It will be this one, and then for D2 I'll be using this and that. Yes, this is how the things are going to work. And now let's write some data. Determinant matrix is, here I'm going to write this one, and I will copy and paste the rest. determinant, what's next? Determinant D1. Determinant D2, determinant D3, and the same here. D1, D2, D3. Let's run it just to see how it will be. So far, this one is not returning anything. Let's return solution found. And shift and enter to make it work. So solve Cramer, coefficients, results. Let's see. Yay! What just happened? Think something beautiful in the result. Determinant 3 by 3 matrix. D3 equals 1, determinant matrix. Okay, now I got it. Like this. Yeah, okay. These are just placeholders, and it was expecting something with lots of dimensions, so it didn't like the ones. So yeah, coefficients of everything is 1 and solution found. This is of course not correct, but the reason that it's not correct is that I haven't written the correct way to calculate the determinant of the matrices. So I'll continue. Just before this, let's write a few ifs and conditions. If determinant matrix equals 0, then we probably are either extremely lucky or extremely unlucky. Then if determinant D1 equals 0 and determinant D2 equals 0 and determinant D3 equals 0, then we simply return infinite number of solutions. On the other hand, no solutions. And if the determinant matrix, this one, is not 0, we will be returning x equals determinant D1 divided by determinant matrix y and z would be determinant D2 and determinant D3. And then at the end we should print something. X equals x, y equals y, and for z it's pretty much the same. Let's see whether it will work. Everything works, and the last thing that we should do is write the coefficients. What we will be writing right now is pretty much this one for DA1, for DA2, and for DA3. And for D, like, we're going to write the corresponding matrices. Okay, let's do it. Just did it for you. So coefficient, I'm just trying to explain once more here what I just write. So this is the D. It's, as you see, the standard matrix 0 0 0 1 0 2 1 0 1 1 1 2 2 0 2 1 2 2 D1. Now the more important part. That's one of the reasons why I named it result and I didn't add it here additionally so it's visible. For D1 the results are here, and then we pretty much copy the normal matrix. For D2 the results are on the second column. We copy the normal matrix. For D3, we do absolutely the same, copy the normal matrix. So now I'll restart the kernel and run all. Now the time is, okay, solution found, and we have this -14, that was the expected one. So yeah, pretty much thank you for watching. I just want to put a few disclaimers. I am aware that like hard coding so much in Python is not a good way for just making some solutions of a 3x3 matrix, but this is pretty much just an exemplary video, so yeah, use it if you want. I hope it helped someone. Thanks for watching, enjoy your day, bye.